So thanks a lot for joining us today. We will be talking about NVIDIA CUDA and basically going through the history of GPUs and GPU programming, because these GPUs have become very valuable and powerful in our modern world for all of us to understand how this technology works. And it's also accessible. As much as these GPUs sound like fancy, advanced technology, it also has its own interesting history, and it's pretty fascinating to learn about. So we're going to start from the very beginning. So computers obviously started with things like transistors and things like that. But eventually, to process this information, something called the CPU was invented, the central processing unit, in the 40s and the 50s. If you remember, some of these first computers were huge, room-sized big computers using vacuum tubes. And the CPU was the main way that they processed information. So they had a few powerful cores, and these CPUs were optimized for versatility and sequential execution. So they're processing things one at a time, but they can also process complex things one at a time. So like a master chef who can cook anything, but they cook a dish one at a time. So those were CPUs, and that's how the computing system started. Eventually, over time, in the 80s and the 90s, video games and 3D rendering started becoming much more popular. So it became useful for us to actually start visualizing the things that we want to see on the computer, because we started with things like terminals, but eventually we wanted to be able to see our output in 3D on our screen, which was much more a user-friendly interface. And also we wanted to play video games and render things like textures and pixels and lighting. And CPUs were because they do things one at a time, it was very difficult to do that, because these pixels, you have millions of pixels on your screen, and to process those pixels, you have to do millions of tiny math problems in parallel. So it's like asking a chef to make a million identical sandwiches, but one at a time. That's going to be much more difficult than having many people make these sandwiches all together. So basically, GPUs were needed for us to start processing these graphics. So in the 90s, they started developing these dedicated chips. Some companies like Asus and even NVIDIA started seeing that it would be important for us to have a dedicated chip that processes these instructions in parallel. And these initial GPUs were specialized for rendering triangles, shading, and pixels. So the core of modern graphics is rendering these triangles, because triangles are the most minimal way of rendering some of the information that we need. And so a CPU has 4 to 6 18 powerful cores, but a GPU can render thousands of lightweight cores. So it's like having many people making your sandwich at once. They can't do much compared to a single CPU, but they're very fast when you do everything in parallel. So yeah, so after these GPUs were invented and they started becoming much more popular, they became mass market, and games like Quake, Half-Life, Unreal, when these games started becoming much more popular, companies like NVIDIA, AMD started also becoming much more popular, because they were mostly gaming companies. By 2000s, NVIDIA dominated. So GeForce cards were everywhere. And if you were a gamer doing gaming in PC, it was still niche. And even now, a lot of people still don't use dedicated GPUs. Some of them are already built into our laptops. But yeah, this is kind of how GPUs became mass market. And these companies were mainly set up as as gaming companies. With the rise of gaming, an interesting thing that happened is that scientists and researchers started to realize that GPUs could be used to solve non-graphics problems. So if you have a scientific or a math problem, what they were doing is they were hacking the GPUs and encoding the math problems as images that you can send through the GPU, and then you read them from pixels. So this was called GPU. I think General Processing, then Graphical Processing Unit, or something like that. So it worked because it's basically, if you have a math problem, and some math problems you need to solve a lot of them in parallel, you could do these kinds of math a lot faster using a parallel process than with the CPU, which could take much longer because you are doing it one at a time. So if you're doing things like physics simulations, matrix multiplications, and the early deep learning experiments, they realized that GPUs were extremely powerful for that kind of work. So now we get to CUDA. which is where NVIDIA noticed that scientists and researchers were basically hacking the GPUs so that they can do these kinds of matrix multiplications and things like that. So they built something called the Compute Unified Device Architecture, or CUDA, which was released in 2006. And basically what it does, it's a programming model. So it's built on top of C, C++. It has a compiler, it has a runtime, and it runs natively on the GPU. So they eliminated the hacks so that you don't need to trick the GPU, you rendering pixels, reading the pixels out anymore. They still kept the normal processing for videos, but now you can also use the GPU for general purpose programming as well, which became very useful. And based on that, CUDA became very popular. So for the first time, developers had a stable way to run arbitrary code on GPUs. Before, you could only run, the graphics, pipeline stuff, rendering shaders and pixels and things like that. But now you can run any program that you want to run on top of the GPU. One important thing about NVIDIA GPU specifically is that they tried to make sure that everything was backwards compatible. So meaning that any code you wrote then will still run today, basically, on CUDA. And then going forward, you can still use the new features, but you can still take advantage of the new features, but your code will also run on older GPUs as well. So yeah, CUDA came bundled with libraries, drivers, and tools to make it much simpler. And we're going to go through a lot of these tools today so that you'll understand better. And yeah, so after that, GPUs also now started becoming used for high performance computing. So supercomputers, instead of using CPUs, most of them started adopting GPUs. And one thing here that also I have a problem with is GPUs, it still stands for graphics processing unit. And the graphics here, I think, is still outdated, but it's a legacy thing, basically. But they do much more than processing graphics, but they're still called GPUs. So scientists are now using CUDA for molecular dynamics, for the simulations, because a lot of these things are perfect for this kind of parallel processing. And so GPUs transformed from things that are used for gaming to things that are used for scientific work. And in 2012, now here's where we now connect CUDA with the AI. Something called AlexNet won the ImageNet competition using GPUs. So these are some of the three biggest scientists or people who started the foundation of AI. The first one is called Geoffrey Hinton. He recently won a Nobel Prize, this guy here, for his work in backward propagation and stuff like that. So it's basically a big deal, one of the godfathers of AI. He was doing a lot of this AI work before everyone else. This guy here is called Ilya Sutskever. He is a co-founder of OpenAI. And right now, he has a company called Safe Superintelligence, where they're trying to do AI safely. And then finally, there's Alex Krivensky. I think that's his name. He actually built and trained the model, him here. So yeah, because AlexNet used GPUs, the other submissions at the time did not use GPUs. They were using CPUs, and this showed the world the potential of GPUs. And because AlexNet was so successful, it was able to differentiate items in an image much better than most other models. Everyone else started seeing the capacity that GPUs have, and then every breakthrough, the GPT, Stable Diffusion, AlphaFold, they all run on CUDA-powered GPUs. But CUDA has, as you can see, it started started a while back. So they have a moat, basically, because if you write CUDA code today, you're pretty much tied to the hardware. Even now on my laptop, on my MacBook, I don't have an NVIDIA graphics card, so I can't natively run CUDA, basically. So every AI startup, every model, every GPU cluster uses CUDA. So yeah, so now we're gonna get a bit into more CUDA stuff, like a bit more into detail. But I don't know, Chris, whether you have any questions or comments or anything there that was interesting.
Yeah, just curious why it will still be dominant, yet it ties you to running on NVIDIA. Does it
Yes,
mean it's still superior?
yes. Yeah, so it's basically like the ecosystem itself. So let's say you're a programmer and you're like, okay, fine. I want to use, let's say you wanted to use a Huawei Ascend GPU instead. So because you're using that GPU, you're going to have to use their libraries and their programming language. And let's say you encounter a bug and you have to fix it. You're going to have to use that community to fix the bug. And you're trying to run, for example, an AI model that was trained initially on the CUDA platform. So it's basically that friction of a programmer. It's basically like the difference between trying to switch from Android to iOS. It's not just that the hardware is a first of all, the hardware is incredible. NVIDIA makes the best graphics cards out of anyone. So if you wanted the raw performance on that hardcore level, you'd need to basically use NVIDIA hardware if you just wanted raw performance. But let's say you wanted now the stuff on top. So the stuff on top, if you wanted the ecosystem and the libraries and things like that, which I'll show you, things like PyTorch, TensorFlow, they're all built on top of CUDA. So that's why NVIDIA has such a moat. Because if you switch to any other type of graphics processor, you would not be able to run the same models or even the same applications on top of any other hardware. They've basically locked it in like that. I don't know whether that makes sense.
Yeah, it does. So there is also value in someone using both the superior hardware and the ecosystem which is already optimized.
Yeah, exactly. Like right now, even in China, I was watching this documentary, and as much as they have other options, there's other options like AMD, there's Intel, but because if you're developing your own AI model, you're trying to train something, because most of this work has already been done. The foundational work, some transformers, so the libraries you're going to be using, the work that other developers have done, has mostly been done into CUDA. Yes, you're gonna have to do the translation work yourself, basically. And ultimately, you're going to run that code on inferior hardware. I think there's still so much value in creating a parallel, system. We don't want NVIDIA to be the only way for you to run GPUs, which is obviously creating bottlenecks for many researchers, as you've seen with geopolitics. It's preventing China from creating the latest AI models, and even us here in Africa is something we have to think about. So yeah, NVIDIA has that moat, but it's also going to be important. And Huawei and other companies are trying. So we're going to see how that's going to go, hopefully in the future. But I have to mention, there's also systems coming up, like one called modular, that allow you to become GPU agnostic. So there's also developers who are building systems on top of CUDA and others that are trying to make it so that you can run your program without having to care whether it's running on NVIDIA or AMD. So there's also progress being made there. So yeah, so now let's get into what actually CUDA is. So when we're talking about CUDA, we're talking about a programming model. So it means that you can just use a normal programming language, and then it compiles. It takes that code and compiles it, and then it's able to run it directly on the GPU. So that's basically what we're talking about here. That's what CUDA is. It's this kind of framework. And then there's two components whenever you're running a CUDA kernel. There's the host code, which there's some code that runs on the CPU that basically manages things and tells the computer what to run on the CPU and what to run on the GPU. And I'll do a demo so that you can see for yourself. And then there's the device code itself that runs on the GPU. So CUDA is basically how you speak to the the GPU's parallel cores. So if you wanted to run a CUDA program, let's say if you wanted to do some addition, you're going to have a CPU part of that program that allocates memory and sets things up. And then you're going to have the GPU kernel that is actually going to do the work in parallel. So let me just come here and show you the demo. So for example, here on my laptop, I'm running a MacBook, and the Mac doesn't have an NVIDIA graphics card installed. So if I wanted to run an NVIDIA program, like even if you're trying to do NVIDIA programming or GPU programming, even if you bought an external graphics card, sorry, even if you have to buy an external graphics card basically for you to do some of this programming, but you can also use something like Google Colab, where they give you a bit of compute. And in this case, I just came here to runtime, and then I said change runtime type. Usually the CPU is selected by default, but then you select a GPU. And then if you run this NVIDIA SMI, you basically get the information about the GPU that you're using. So if you wanted to easily test on a GPU, you can use Google Colab. And now we are going into the details of how exactly an example kernel or GPU program works. Yeah, so now we're actually going into an example of how a CUDA program actually works. And I'll explain everything so that you understand. It's very simple. Runtime disconnected. Okay, no problem. I'll just close this like this. We don't need to run. So basically, we selected our runtime here as a GPU. Okay, that's where we can run an NVIDIA GPU, where we can run these these CUDA processes. And the goal of our program is going to be very simple. So we are writing a program here that is going to take two lists of numbers. Okay, so you're going to have two lists of numbers. Let me show you an example. So we're going to have two lists of numbers here. Okay, so two lists of numbers, and each list is going to have 5 items. Okay, and what we want to do basically is to add these up. We want to write a program that is going to add these up. It's going to take 10, it's going to add 1, 20, it's going to add 2, 30, it's going to add 3, and then it's going to store those answers on a new list for us, basically. But the special thing is, it's very easy to write this in a parallel way. Like, I'm sure you can easily imagine how to do this in a normal programming language like Java or JavaScript or anything like that. It's very simple. But what we want to do here, we want to use CUDA to do all of this in parallel. So we are going to spin up 5 GPU processes that will do all of these in parallel. 1, 2, 3, 4, 5. Okay. But now let's back up a bit. So the GPU function is called a kernel. It runs directly on the graphics card. Instead of one worker doing all the work like the CPU, the GPU will launch many workers or threads at the same time so that it will add them up. Each worker that is launched will get an ID number and will handle a small piece of the job. So just for your clarity, let me just zoom in a bit here. And then this is the actual GPU kernel code here that we will be running. Okay, so each GPU worker, it knows its own ID. It will make sure that the ID fits inside the list size. It will add one number. So that's all the GPU will do. It will take one number from our first list. It will take another number from our second list. It will add them up, and then it will store that result in a new variable called C. And then into the list C. I added a helper here to check for CUDA errors while I was debugging. CUDA by default is silent, but you can add your own error checking. This doesn't matter for now. And now this is the main program that runs on the CPU. So we mentioned that when you're running a CUDA process, there's the CPU part and the GPU part. So what will the CPU part do? It's going to prepare the data. It will send the data to the GPU. It will tell the GPU to do the work, and then it will correct the results back and print the results back to us. So we start with a constant, the number of elements in our list. We said it's 5. And then we're going to create these two lists on the CPU. Okay, so we create our first variable, 1, 2, 3, 4, 5, the first list of numbers, 10, 20, 30, 40, 50, second list of numbers, and then this is an empty list where we'll put our results. We're also going to create some space for these lists on the GPU. So create some pointers, and then how much space we need, 5 integers. And then we ask the GPU for space for the 3 lists. So, you do it like that. Then, since we created those lists on the CPU, we are going to copy that data from the CPU to the GPU. So just like this. This part's, it's okay. This we don't understand what things work, but then you understand we copy the data from the CPU to the GPU. And then now here's the important part. So we're going to launch the GPU kernel. We launched our group of workers. So here we're going to launch 5 workers that will each handle one addition at the same time. So N1, 1, comma N means 1 block and then a group of workers. Remember N was 5 here. So it's going to do 5 workers each that will handle the addition. And then it's going to take our list, our A list, our B list, our C list, and the number N, the 5. So then it's important for you to wait for the GPU to finish, because sometimes these processes can happen because they're happening in parallel. This is also going to be important, because if you just try to print out the result immediately, sometimes you're going to have an error. And then finally, you copy your results from the GPU to the CPU once the results are done. So here you remember, now we can go back here and check and go back to our GPU kernel, our method for adding. So it takes an integer A from the list, takes an integer B, then the C, and then it takes the number N. So it loops N times, 5 times basically, and then as you remember, it adds one number from the list A to list B and then writes it into C here. And then it's going to return from the GPU, and then we come back here to the CPU. And then here we are, check CUDA. And then finally, it's going to print our results. And from this list, as you can see, 10 plus 1, 11, 20 plus 2, 22, 33, 44, 55, and that should be what we expect. And then finally, it's also important to manage the memory and clean things up, and then it's done. So once you've written your GPU program, there's a way that you can run it. Some of these are optional, but you essentially click this. I don't know whether my runtime is still available. Yeah, now it's connecting. It could take some time, but I already ran the results. So what we expected, this is our GPU process here. This is our GPU, the details of our GPU and the processes. But the result it eventually prints is 11, 22, 33, 44, and 55. And this is basically a simple program to show how you write a GPU kernel. But for the most part, as I'll also demonstrate, you never need to go this deep into CUDA itself. And it'll answer some of those questions about why CUDA is so popular. It's because so many things have been built on top of CUDA to make it easier for programmers so that you don't need to do all this work yourself.
So in a way, this looks like a lower level implementation where you have to manage both the CPU and GPU on your own.
Yes, exactly. Yeah, as an example to show you now the hardcore CUDA code and what exactly happens. Yeah.
Okay.
So now that we've seen how how you do a CUDA program, we've done this vector addition. You've seen the CPU allocates memory and sets things up, and the GPU does the work in parallel, which is very good. So now to go deeper into that pipeline. So what was actually happening there? So we wrote our CUDA code in C++, and then there's an NVIDIA CUDA compiler. That's what this is. It takes that code and then it breaks it down. So the NVIDIA CUDA compiler breaks it down into PTX, which is basically turns it into more assembly languages and GPU machine instructions, and then executes on the hardware. So that's basically how the CUDA pipeline works. You take your CUDA code, compile it, and then you execute it on the hardware. So CUDA abstracts all this complexity, but it's there under the hood. To prevent, now you don't need to do all this stuff yourself. Basically, when you're doing normal machine learning research, you don't really need to go into the GPU and the CPU yourself. So there's been libraries that have been built on top of CUDA, and this is where we start creating the NVIDIA moat. So you have CUDA for linear algebra, deep learning, thrust, tensor. So you basically turn things that you don't need to do commonly, matrix multiplication and things like that, and then you turn them into libraries so that a developer can just come with their need. They easily use a library instead of having to manage all that themselves. So all the memory, GPU stuff, CPU stuff is handled by some of these libraries, and they're heavily optimized and updated with each GPU generation. So most AI code isn't handwritten kernels. It's just calls to these libraries, which then call CUDA. And then now on top of those libraries, there's even more abstraction. So now, Python is usually called the language of machine learning. And this is partly why, because we have a lot of Python wrappers that make CUDA accessible without having to touch C++ yourself. So now we're even abstracting even farther away from the C++. So there's things like PyCUDA and Number. So you can write CUDA kernels in Python, and you can even process lots of CUDA stuff without ever having to touch C++. So now there's even libraries that abstract that stuff. So Python is it's a bit more high level, but then it goes down into the C++, and then down into the CUDA, and then down into the GPU itself. And now, or even on top of the Python abstractions, the Python bindings, there's even more abstraction built on top of that. And now these are machine learning frameworks. Now we're getting into things which people are more familiar with, things like PyTorch, TensorFlow, JAX. So now you take even more abstraction and you make it even easier for developers now, so that the developer usually doesn't They don't want to deal with the CUDA kernel themselves. They're more interested in, can I build an AI that can learn from these bunch of images, and then takes those images, processes them into a transformer, and then does this. So you have your Python. It uses PyTorch, which uses the CUDA DNN, which goes into CUDA and then goes into the GPU hardware. So this is how kind of the abstraction works. You start from the low level, and then we've built a whole ecosystem around CUDA, which goes into Python, PyTorch, TensorFlow, and everything, basically all the modern tools that we use to train AI models today. And that leads to a whole ecosystem built around CUDA, including things like Hugging Face transformers, Keras, Lightning, Fast AI, high-level training APIs. So even what OpenAI uses to train ChatGPT, and what we use for things like Stable Diffusion, Midjourney, all the AI models that we see basically use form or another of these kinds of CUDA abstractions, basically. But what these companies do is some of them they go really down into the low level, and they write their own kernels. They really customize these AI models for themselves, and it's because you really understand the entire pipeline, and it's also possible for you to go down into the lower level and optimize the CUDA kernel so that it's much more efficient compared to what you can get off the shelf and the libraries that are usually provided for you. So now we can finally connect the dots. So we start with the CUDA kernel, or we start with the GPU. Basically, we start with the hardcore GPU that, as we saw, it can process multiple things at the same time. And then on top of that, you put your CUDA kernel, your C++ code. But then on top of that, there's some libraries that NVIDIA has written. And then on top of those libraries, you build frameworks like PyTorch. And then on top of that, you build something like a transformer. And then on top of that, you have your service. Now you can connect that to an API. You connect to an API, you build a product around it, and you can call it ChatGPT. So when you ask ChatGPT a question, somewhere deep down, it's just a CUDA kernel multiplying these matrices on an NVIDIA GPU. Basically, that's what's happening. And this is partly why NVIDIA is so sticky, because they've built essentially an entire pipeline for machine learning engineers. And for you to replace this whole process, you're going to have many more technical issues. You're going to have to slow down. You're going to have to do this. You're going to have to do that. But as I mentioned, we're also making progress. Like recently, even DeepSeek, they announced that they had optimized some of their models to work on some of their local GPUs, which was good news for the local GPU market.